Welcome to the dOrg hot seat. Blockchains are deterministic. In EVM chains, you put code, it gets processed, you pay gas for this computation, and boom! All nodes should have the same result. They have their limitations though. You need to write in Solidity or Viper, and computation is expensive. Our guests today, Carlo and Gabriel from Cartesi, have a different approach. They give you a Linux runtime so you can compute anything. They have made it deterministic though, so computations are replicable and verifiable given the code and the inputs. And then they implemented a challenge system to make use of this replicability to create a trust model. Speaking of trust, by now you should be seeing where the dOrg hot seat is going. We're opening sessions to go beyond the dOrg all hands and invite listeners to ask live questions as well. So follow us on Twitter at dOrg_tech to see when these sessions are going to be. You don't have to trust us to ask the hot questions. You can come and ask them yourself. We would also like to thank those who trust us enough to donate to our Giveth campaign at giveth.io/project/dOrg-hot-seat. That is giveth.io/project/dOrg-hot-seat, and keep the lights on this show. Let's get started with today's wild idea of a Linux runtime rollup with Carlo and Gabriel from Cartesi.
Sure. I prepared a very short and sweet presentation for you guys to give it a sense of what we have here. And that is intentional, so you can kind of grind us afterwards. So we are ready for that. We love to receive the harder questions. So today here, like you introduced, it's me and my friend Carlo. We both work at Cartesi for a long time now. And I'd like to introduce what Cartesi is at first. So it is a app-specific rollup, optimistic rollup, that uses a RISC-V implementation of a processor to build a VM that supports the Linux OS. Okay, that is a lot of things, right? So how does it look like? How does that mean for the developer? So we got to Ethereum, and there's a lot of things about it, right? It's a whole new industry, and with that, we got reduced to a toolset that is very small. I've been coding on Ethereum since 2016. Things came a long way, but still, it feels like we have pliers and very simple tooling to manage to recreate the whole world, right? Like people have been trying to disrupt all the industries only using the simple toolings. But if you have the support of a whole OS, what can you do? What can you have? What can't you have, right? Like we've been developing web technologies. We've been creating these ever more complex ways of creating systems like microservices. We have access to databases. We have access to so much good stuff that we spent thousands, millions of years with of people's lives, right, developing, and we kind of threw it away for a little bit, but Cartesi is trying to bring it back for the development of blockchain itself. So it's very incomparable. And here's a very small example of a string replace done in Solidity. I mean, it's not really readable at this size, but the idea here is just to show how complex this thing is. And there's a lot of assembly happening here as well. And that's just to be doing a very simple thing that many applications do every day, right? And even if you take this as is, it is very expensive. It takes a lot of your contract space if you don't use it as a library. It comes with a lot of problems. And if you're trying to do this currently, you could just use Python replace function, and it becomes like very, very easy again to do something that we learned very early in universities. And what about the computation itself? So if we have variant gas that you can have as maximum for a block, we are not even talking about the actual monetary costs here, right? I'm just talking about the possibilities. and still being very generous. Let's say we can do a function that only uses the add opcode. So that's 3 gas. So that means that at best, and that's very generous, do a 10 million instructions on a single. And that is good for many things, but it's very limiting as well, right? It's difficult to express the whole human interaction complexity with this kind of a machine. But in a 13 seconds, and we limit it here just so we have a base to compare with Ethereum, which is the time for a block in Ethereum, sort of. On a laptop, in a simple laptop, we do 3 billion instructions. And this is a screenshot of a Bash interactive shell inside a Cartesi machine. So here we are being very, very, how to say, not generous with the Cartesi machine. And just to make it easier for you guys to understand and visualize, the little yellow square there would be the capacity of Ethereum compared to this Cartesi machine example right now. That's how far you can go if you use a rollup using the Cartesi rollup technology. And here we have some examples of things done and built in hackathons or side projects or even grants of the Cartesi community. Carlo should comment on those.
You're going to take it over right now. So as Barros said, the Cartesi machine offers this rich environment because after all, it's a Linux machine on a RISC-V ISA. So basically everything that you can run on RISC-V, you can run inside the Cartesi machine. So these are a couple of interesting applications that are built using Cartesi. So top left, we have a parking application. So it's a common problem. There are multiple solutions in Web 2. But there's always the problem of you have to put money on specific systems. They don't interact with each other. Each place has its own rules. You have to figure out what's the system you have to use. So these guys from Poland, they just made a system that whoever wants can use. And if you have traffic, a problem, like you get a fine for parking somewhere and not paying, well, you have a decentralized trustless application that can show you, yeah, I was parked in there, but I was still paying for it. And you can get a proof that you were within the allowed period for you to park, given the amount you paid. And that would be pretty hard to implement directly in smart contracts. But once again, the Cartesi machine is a Linux-enabled machine with a lot of computational capacity. So these guys, they just use the JSON libraries to calculate coordinates within a polygon and this kind of stuff. Databases like SQLite, and they managed to implement it pretty quickly. The example underneath, it's a Mandelbrot fractal. And these Mandelbrot fractals, they demand a lot of computational power, right? So these guys from a hackathon, they said, okay, let's make a NFT collection in which you can prove the art that was generated. So they use this Mandelbrot algorithm within the Cartesi machine. They've done it in Rust, and they generate these beautiful fractal patterns. And unlike most NFTs that you just have a certificate of, you can change, you can delete. On this case, the art was generated within the Cartesi machine, so everyone can validate the art is being generated correctly, can reproduce it, and can make sure it's the right one. In the middle, I think most of the people are familiarized with that screenshot. That's Doom. So there was this guy on Twitter asking, hey, if Ethereum is really the global computer, why don't we see Doom on it? And then we had this guy from our emulator team, Eduardo, and he said, okay, challenge accepted. And he made the Doom run in real time inside the Cartesi machine. So there you have a Doom screenshot he took with the Cartesi machine console behind running the Doom. You can take a look at his Twitter later. I can give you the URL so you can check the video and even the repo on yours. On the top corner, we have a much different application. So this guy was dealing with the problem of fingerprint identity. And in multiple places, it's used for clocking in and clocking out and other things. And people are used to tamper with it. So they go into a fingerprint scanner and they use a silicone fingerprint, or they use a photocopy or something like that to tamper with it, to say they're there, while they're not, to clock in, clock out for teammates, stuff like this. And these systems also have a problem because they put someone to watch these people and validate they're there, but in corrupt setups, these people start asking for bribes, and then they say you're there if you pay, they say you're not if you don't pay. So this guy made this decentralized application with Cartesi, and the input is the fingerprint, and then you got this C++ program using OpenCV that processes the fingerprint and extracts an array of features describing it. And then he feeds this array of features into a machine learning model he trained to classify if the fingerprint was spoofed or not. And this is running inside a second Python program. And then if someone says you're trying to tamper with the system, it's not because they asked for a bribe and didn't pay or anything like that. It's because you have a model running inside a machine transparently. Anyone can just reproduce it, can dispute if someone makes an incorrect claim and show the correct outcome. Then on the right, top right corner, we have a game, which is this guy got this retro emulator, like fighting game style, like Street Fighter, Tekken, stuff like this, Ikemen Go, and he made a Python program that feeds two fighters that are NFTs. And in this case, we have Pichu and the Kung Fu guy, but there are multiple different ones. He made a pizza delivery guy. He made animals, all sorts of stuff. And this application is called Colosseum. So you have the fight. People wage on who's gonna win, and then the fight happens within the Cartesi machine on this retro fighting emulator, and then it renders the fight and they pay the winners. And once again, if someone tries to tamper with the result, anything, you can just dispute because it's running inside Cartesi machine, and you can use the protocol to make sure the correct result is enforced. Bottom right is a mashup of two games that are well known, so Candy Crush and Pokemon. So we have a Pokemon-like game in the blockchain, which is Axie Infinity, but it's actually centralized. So the NFTs are on-chain, but the game logic itself is basically centralized, and that's because you don't have computational power on the blockchain to support a game like this. So these guys with Cartesi machine, they do have the computational power and they do have the tooling to express complex logic. So they developed the game simulation logic in Rust, and it runs inside the Cartesi machine. And then they have the made in Unity, which has 3D graphics, all the goodies, and that display this fight between the characters, powered by moves on this Candy Crush-like shared puzzle. Once again, everything is transparent. If you have a competitive gaming landscape, there's no admin that can tamper with a random number on the server or can tamper with the match or do anything nasty. Everything's transparent. Anyone can verify the computation and can dispute it. And the last example I want to talk about is the one on the back, which is a DeFi one. So these guys, they were inspired by the Mango hack that happened last year. So this guy pumped an asset, then goes to Mango, asks for a loan of stablecoins, use the pumped asset. Mango goes to a price oracle, it checks out, gives them the lending, and then they don't pay. They don't pay, but when Mango tries to liquidate the collateral, it's not worth the amount they got. It's actually worth much less because the asset doesn't have a liquidity, so it's highly volatile. And inspired by this, what they did is they made this application called Nucleus inside Cartesi, which receives a stream of data containing the volumes and prices of assets being negotiated. And then they can use NumPy to make an analysis on what's going on. And they can come up with better risk metrics and output things to a lending protocol like, yeah, you cannot lend more than $10,000 on this asset because if you try to liquidate it, it won't hold. Or yeah, this asset is great, it has low volatility, it's It's got great liquidity. You can lend 2 million, and it's no issue if you have to liquidate because the price will hold. So these are a couple of interesting applications being built with Cartesi, just to give examples of neat stuff you can do when you enable your applications with all the goodies that have been developed on traditional stacks up to today.
We are open for questions.
All right. Thank you very much. Thank you. That was a great presentation, very short and sweet. I'm going to get started with the first question. In Ethereum, we know where the computation happens, and it's replicated in every node. Where does the computation happen in Cartesi?
So the way the Cartesi ensures that computations that happen off-chain inside the Cartesi machine are actually secured, even though they're validated by a smaller amount of nodes, is that we have this protocol, which is called the verification game. And what happens is that whenever someone doesn't agree with the outcome of computation, they can just engage into this interactive protocol and actually use the underlying chain like Ethereum with thousands of nodes to check who actually is correct on that dispute. So it's not a matter of arbitrating with a small amount of nodes. Arbitration actually takes place on Ethereum, which is where our protocol executes, right? So how does this work? The Cartesi machine itself is deterministic, and that means that if you have two parties not agreeing about the outcome of computation, that means that at least one of them did something they shouldn't. So the first part of the protocol is actually identifying the first state change on the Cartesi machine that led to a state that parties didn't agree. Translating, that would be the first RISC-V instruction, in which both parties agree on the Cartesi machine before executing it, but they don't after. And once we find that instruction, what we do is we had this major work of implementing a Cartesi machine emulator on-chain in Solidity. So when we reach that instruction, we ask this on-chain emulator, which is the consensus of Ethereum or of any underlying chain, to execute the instruction and to tell us what's the correct state after that instruction is executed. If it matches the original claim, then it's fine, you won the dispute. Otherwise, you lose. So that way we can have this smaller set of nodes validating these extremely heavy applications with a lot of computation, but still maintain the guarantees that a single correct party can enforce a result, because we go back to Ethereum security to arbitrate disputes when there's need.
Apps can operate on dedicated rollups, and they rely heavily on off-chain computations, right? So how does Cartesi ensure the integrity and security of these computations? So what mechanisms are in place to prevent potential attacks such as data manipulation, false reporting, etc.? Can you discuss a little bit the validation or challenge processes in place to ensure the security and trustworthiness of the off-chain computations?
So currently the framework enforces that all the inputs for computations must be available on-chain. So that way we have guaranteed that no input was tampered with, and also that there are no data availability problems, right? Because if I want to reproduce computation that you performed on a file on IPFS, for instance, and I claim that that file is not available, but you claim that the data is there, there's no way for the protocol to arbitrate what actually happened, right? From the blockchain point of view, you cannot tell if someone is lying about having data available somewhere else, or if the other person is lying about not being there. So since this is a really hard problem currently, all the inputs, they are available on-chain through a special smart contract on our framework, which has a method called add input. So whenever you want to feed something to the Cartesi machine, you must provide that input through this smart contract, and then there's no dispute about inputs. If it's in there, it's in the blockchain. If it's not there, it doesn't exist.
Aliás,
Related to the topic we were talking before on AI, on the light of the different models that you can run on CPUs like Llama, Vicuna, GPT-4o, the different models like Groovy, Do you think these models can be run on a Cartesi virtual machine? And what do you think about it? Why would it be important if you can do it?
For sure, you'll be able to run these on Cartesi. These large language models, they just need a lot of processing. Cartesi machine can provide that. In fact, just now at East Lisbon, one of the hackathon winners and finalists at the main track called ChainGPT was a project that used the alpaca model for answering questions just like ChatGPT. And the importance of this is to have accountability on the actual information provided. So as you're running ChatGPT, you're trusting OpenAI to be providing you with the right answers. Not in the sense that the model cannot make a mistake, but for instance, if you ask ChatGPT what is a good drink for your health, you shouldn't be just going and answering Coca-Cola, right? And if it does, you should hold OpenAI accountable for that. And remember, kids might be using this model, so in these settings, it's more interesting for a school or for parents to be using a system that is reliable enough and trustworthy, such as a model running on blockchain, so they know that the model hasn't been tampered with.
Drew, huge work of re-implementing the Cartesi machine in Solidity. So once we have this single instruction in which we know the parties disagreed, we ask this on-chain Cartesi machine emulator to execute it, and then to tell us what's the next state Merkle hash. If it matches the guy that claimed the computation result match, then he wins the dispute. If it doesn't, he loses the dispute. So this way we can have a really small set of validators per application, but still have the security that a single party can enforce the correct result. Because when there's a dispute, it's settled using the same security guarantees that the underlying chain provides.
All right, excellent. Thank you. Nick, I think you can just hop on and have a follow-up question on this.
Hey guys, yeah, I really appreciate you guys taking the time and going through Cartesi platform, and seems very interesting. And you know, it sounds like you've touched on some of the security questions I had already, which is great. You know, it really seems you guys, you know, provide a unique approach to off-chain computations, and you know, where every dApp can essentially operate on its own dedicated rollup, and you know, minimizes resource cannibalization, right? And but it does bring to light some of the potential security or even integrity concerns, right? You know, whether it be data manipulation, you know, since computations, you know, they're carried out off-chain, you know, how do you safeguard against malevolent actors attempting to manipulate the data before it's even committed to the chain, you know? And how does Cartesi's machine detect and handle any discrepancies in the computation process, you know, ensuring that the data is, you know, in fact being processed the way it needs to be? And you know, the second part of that I just wanted you to touch on is, you know, what measures, you know, have you put in place to prevent nodes from reporting false computational outcomes back to the main chain? You know, are there like any consensus mechanisms or, you know, verification processes utilized for validation before the outcomes are even accepted? You know, I just think you know, this in the blockchain world, I guess we all kind of are somewhat aware, and we appreciate the fact that you know, there's always this security / scalability trade-off, right? And you know, I'm just curious to find out what you guys think about ensuring security and integrity, you know, when it comes to this type of trade-off, you know, with scalability in this space. You know, how do you balance these factors, you know, in the environment, and make sure everything's secure and capable of handling large-scale computations?
So Nick, I'm gonna explain a little bit. I think you have a good point, but since you touched many points on your question, if I leave something out, please ask me again. But mainly, it's not that different from other rollup solutions. So what you have is, for instance, data availability needs to be ensured on this layer. That makes things. So if you have all the input, they think of, I mean, all optimistic rollups, they start off from the premise of having at least one honest validator. So it's up to the application itself to ensure that the economic incentives are aligned with that as well. So maybe you as a user don't want to run a full node all the time for your interactions with a specific rollup, but at a certain point in time, you're interacting with that. You have some financial incentives to ensure that at least you're in your own node, you can verify things like that and post to the chain claims that things are wrong. And with that, you can possibly slash bad validators, bad actors in general. Remembering, again, the Cartesi machine is completely deterministic. You have the program that is running and the input and can reach to the same. Does that make sense?
Yeah, it does make sense. Thank you.
Yeah, just adding a couple of points there. So as Bob said, all the inputs come through the blockchain, so there's no data availability problem. You cannot argue that you can reproduce computation because data isn't available, or that someone tamper with the data or anything like that. So already solves that stuff. And the other thing is, the machine is completely deterministic. So RISC-V itself, it's not, but the way we emulate is, so wall clock, it's deterministic. It always starts from the same zero epoch, 1st January of 1970. Floating point operations, which are inherently not specified to be deterministic. So there's a lot of hardware state that can change things. You multiply two numbers, the float pointers in your machine, 10 times in a row. The last significant digits will change because it depends on the hardware state it was. It's not specified behavior, right? So we emulate those in a way that it's deterministic using soft floats, all this kind of stuff. But it was a lot of work to make the Cartesi machine itself deterministic, and then a lot more work to make the on-chain implementation 100% equivalent. Because if it's not, then it's a surface of attack that someone can actually win a dispute when they're incorrect, right? So I think we answered your question, but let us know if there's a point we left out.
Yeah, no, that definitely clarified things for me. Deterministic validation mechanisms. Yeah, that definitely makes sense.
Great.
So I assume that you guys chose RISC-V because that's open source. But what are challenges on trying to recreate and emulate this architecture, and how long did it take, and what were the resources that it took?
So the core tech, which is what we call the on-chain emulator, plus the implementation of the protocol, plus the Cartesi machine off-chain with the components of the node that makes the stuff execute Cartesi machine, make a claim on-chain, and verify other computations that are happening, dispute them, all this stuff. It took us quite a while. It took us like 2 to 3 years to develop.
All right, that is all today for Cartesi at the intersection of a Linux virtual machine, a deterministic Linux virtual machine, and blockchain. Thank you to all the members for their amazing questions, and thank you to Cartesi for coming up here and sitting on the hot seat and responding them all.